Gases are all around us. No, literally. At this exact moment, there are gas molecules surrounding you. Every time you breathe in, you're inhaling the various different gases that make up the Earth's atmosphere. And every time you breathe out, every time you sing, you are dealing with gases, even though you often can't see them. Sometimes we can see gases. For example, we can see smoke and we can see steam, since they are gases with solid or liquid components suspended within them. And sometimes gases are just colorful, like this toxic gas, chlorine gas. The point is, there are gases all around us, and it is critical that we study them and understand how they behave because they have such a huge impact on the Earth. In this video, I'm going to be covering the 4 main ideal gas laws, and the first one I want to talk about is known as Boyles Law. Boyle's Law was named after the scientist Robert Boyle, which you can see here. But like most scientific discoveries or laws, Robert Boyle didn't actually discover the relationship known as Boyle's Law. Richard Towneley and Henry Power actually discovered the relationship first. And what they found was that pressure and volume were inversely related. This meant that if you increase the volume of something or a system of gases, you will decrease the pressure. They're not directly related, they're inversely related, and vice versa. So if you decrease the volume, you'll increase the pressure. And so when we talk about Boyle's Law in chemistry, we usually refer to it by this mathematical expression, P1V1 equals P2V2. And what this means is that the pressure times the volume at an initial condition will equal the pressure times the volume at a second condition, or later. So if you know the initial pressure and the initial volume, and then you change the pressure to something and you know that value, you can solve for the volume at that second condition because you have 3 out of the 4 variables, just by rearranging the equation with simple algebra. So here's a demonstration of Boyle's Law. This glass container is connected to a vacuum pump. You can actually see the vacuum pump in the background if you look to the left. When turned on, the vacuum pump essentially sucks a lot of the air out of the glass container so that the pressure inside the container lowers. Though, I don't actually mean the word suck. Suction doesn't exist, and if that surprises you, you should check out my video on this channel that covers this misconception. Anyways, so according to Boyle's Law, pressure and volume are inversely related. So if I lower the pressure inside the glass container, what should happen to the volume? Well, it should increase, and that's what happens. Here, let's speed this up. Now, if I had a really powerful vacuum pump, I could decrease the pressure inside the container so far that the balloon would pop. The material of the balloon can only stretch so much, so there's a limit to how much the volume of the balloon can increase. Now, what should happen if I open the valve and let air rush back into the container? Well, the pressure should increase and the volume should decrease, just like Boyle's Law predicts. Sure, let's say now you know that there's an inverse relationship between pressure and volume. But you may be wondering right about now, why? Why does volume increase when pressure decreases and vice versa? What's even happening on the molecular level? To understand this, you have to remember the kinetic theory of gases. There are many small, tiny gas molecules flying around, moving around in a container, such as a balloon. A balloon can be a container. And all these gas molecules are moving around at high speeds, bumping into each other and the walls of the container. And so here I drew arrows pointing to the walls of the balloon. So these are the gas molecules, the little dots flying around or moving around in the balloon, and then occasionally they hit the walls of the container. And this is what contributes to the pressure inside the balloon. But there are also gas molecules on the outside of the balloon, from the atmosphere, because there's gas molecules all around us. And these gas molecules are flying around and occasionally bumping into the outside of the balloon. And so we have pressure on the inside of the balloon and we have pressure on the outside of the balloon. In the demo I just showed you, I decreased the pressure on the outside of the balloon, but the pressure inside the balloon stayed the same because the balloon was sealed. And so the pressure inside the balloon was greater than the pressure on the outside of the balloon, so the volume of the balloon increased, and so it expanded. Before, when I didn't mess with the pressures on the inside and the outside were in an equilibrium, so the volume of the balloon stayed constant. But once I decreased the outside pressure, you can think of it like a tug of war. If you look at the arrow size, the arrow on the inside is greater than the arrow on the outside, and so the balloon had to grow to get back to an equilibrium state. There are many real-life applications of Boyle's Law. For example, every time you breathe, you are using the ideas of Boyle's Law. And so, I don't know if you've ever thought about how you breathe before, but basically what happens is your diaphragm lowers, which is that darker pink shape there in this visual. Your diaphragm lowers and your lungs expand. When your lungs increase in volume, well, the pressure decreases inside your lungs. And air likes to travel from areas of high pressure to areas of low pressure. And so when you breathe, you create this sudden area of low pressure in your lungs, and there's higher pressure out in the atmosphere around you. And so the air right in front of you will travel into your lungs because it likes to go from high to low pressure. And here's just another video showing the same thing. The diaphragm is supposed to be the bottom of this glass container, and so I'm lowering it with my hands. That's your diaphragm lowering, and then your lungs expand because air rushes in. The next two laws I want to talk about are very closely related. The first one I want to talk about is known as Gay-Lussac's law, and it is credited to Joseph Gay-Lussac. Basically, Gay-Lussac's law relates pressure and temperature together, and this time it's a direct relationship. So when pressure increases, so does temperature, and when pressure decreases, temperature decreases. That's what a direct relationship is. And so when we do math problems dealing with Gay-Lussac's law, we write the expression as P1 over T1 equals P2 over T2. So what's happening at the molecular level? Well, when we are talking about Gay-Lussac's law, we are assuming the volume is constant, the volume of the container. And so if I draw here a sample of gas in a fixed volume container, there will be gas molecules, these little dots, that are moving around and bumping into each other and into the walls of the container, just like we said before would happen because of the kinetic theory of gases. And when we add heat, the speed of the molecules will change. It will increase. That's just a property of gases. So when we add heat, or we increase the temperature, the particles will move faster, the molecules of the gas. There'll be more collisions with the walls of the container, and when there's more collisions, there's greater force and there's greater pressure. So you can see now, by increasing the temperature, we can actually increase the pressure of a sample of gas. Have you ever noticed that your check tire pressure light comes on more often in the winter months? This is because of Gay-Lussac's law. In the winter, the temperature of the outdoors is lower, and so the pressure of your tires is lower. A pressure cooker is another good example of an application of Gay-Lussac's law. So how a pressure cooker works is you put your food inside of this fixed volume container and you start heating it up. And so the gases inside this fixed volume container gain energy, gain heat, start moving faster, and so the pressure inside of the pressure cooker increases, and so then the food can be cooked faster. The third law I want to cover is known as Charles's law, and Charles's law is named after the French scientist Jacques Charles for his work during the 1780s. What Charles's law describes is the relationship between volume and temperature. So Gay-Lussac's law, which we talked about just briefly before, related pressure and temperature, and there was a direct relationship between pressure and temperature. Charles's law is very similar, but it's describing volume and temperature. There's a direct relationship between volume and temperature according to Charles's law. When volume increases, temperature increases. When volume decreases, temperature decreases. And so we write it in a very similar way when we're dealing with it as a mathematical expression. We write it as V1 over T1 equals V2 over T2. Charles's law assumes that the pressure is constant. So if you have some container, like a balloon, that has a sample of gas in it, like we've said over and over again, there are gas molecules inside of this container that are going to be flying around and hitting the walls of the container. If you add heat, they'll just fly around faster, but this time the pressure is constant and the volume can change. And so to compensate for how hard these gas molecules are hitting the walls of the balloon, well, the balloon will grow and get bigger. It's like a force is pushing the balloon from all angles inside, making it grow. Because of Charles's law, we can have hot air balloons. To get a hot air balloon to float, we have to turn on this giant flame and heat up the air inside the balloon. And once the temperature of the air inside the balloon increases, the volume of the gas or the air inside the balloon increases. And that's how it floats. Like all the other laws, Charles' law works in the reverse. So if we decrease the temperature of a gas sample using something really cold like liquid nitrogen, the volume of the gas sample will decrease. The last law I want to cover is known as Avogadro's Law. Now that name might sound familiar if you've learned a thing or two about moles. You see, we refer to the number 6.02 times 10 to the 23rd as Avogadro's number. And essentially that number is just the number of atoms or molecules in 1 mole of a substance. You see, the same Italian scientist, Amedeo Avogadro, was credited to Avogadro's Law, which relates the number of moles of a gas sample to the volume of the gas sample. And just like the last two laws, this relationship is a direct relationship. So when we increase the number of moles, we increase the volume, and when we decrease the number of moles, we decrease the volume. And so we write it in a really similar way when we're working with it in math problems. We write V1 over N1 equals V2 over N2. And remember that N stands for the number of moles of a substance. Okay, so I think this might be my favorite gas law because I think it's just the easiest to comprehend. The idea is that if we increase the number of moles, we're basically increasing the number of stuff in something. And stuff takes up space. So if we put more moles into a balloon, it's going to need to have a greater volume. You can think about it on the molecular level. There's more gas molecules in this balloon, and so they're hitting the walls more, and so it's greater number of collisions, and the volume can change. But if you just think about it, it's more stuff takes up more volume. Every time you pump up a flat soccer ball, you're applying Avogadro's law. You're literally adding more gas molecules into the container, the soccer ball, so the volume increases. And in the reverse, if you let out the moles of gas in a container, the volume decreases.